our last topic in this course, separation processes. And we are going to discuss drying operations as a separation technique in this course. And then we will be done with all the separation techniques that we would like to discuss in this course. So before we have 1 minute left, so I just would like to ask you that if you have any questions that you would like to ask before I start discussing the drying operations. If you do not have any questions, then I will start discussing the drying operations, which is our last topic in this course. And from next week, you will be working on the lab assignment. And the lab assignment will be on distillation processes. So my suggestion is that all of you should learn about the distillation, read the chapter, read the material that I have already provided, work with those recommended problems that I have shared in Canvas. It will be much more easy for you to perform the lab assignment next week. So next week there will be two sessions. One session will be on theoretical calculations around distillation, and there will be another time when you will be making some more calculations based on the actual data. Jorgen is planning to make a video on distillation, just to show you that how the distillation equipment looks like, and how it works, how you can calculate the so not calculate but measure the steam pressures, and how you can measure the different controls in distillation. So hopefully he will be ready with the video soon, and it will be uploaded into the Canvas. But again, as I suggest, that it's good that before you come next week, it is important that you read about distillation in more details. Then it will be much more easy for you to solve the lab assignment. One more thing I would like to add before I start discussing the drying operations. I could see in the Canvas that there are a couple of students that who have not assigned themselves to a particular group. So for those students who have not assigned themselves to a group, it is better that you do it as soon as possible, or we can just put those students into the groups which are not filled yet. So you will be working in groups of three members, and you will be working on theoretical calculations early next week, right? So more information on the lab assignment, I will try to send you by tomorrow, or maybe by Wednesday. So it would be good that you will be prepared before you come next week. So now I'm going to start my discussion on drying operation. Drying is a very important separation technique in chemical process industry. We use drying operations in many industrial processes, like the region where we are, we have a large number of pulp and paper industry. And in those pulp and paper industry, drying equipments are one of the most important equipments. And those equipments helps us to dry our paper, dry our board, and dry our many different types of paper products. So we use drying in the paper industry. Many food industries, they use drying. Many pharmaceutical companies, first they make a reaction to produce a certain drug or a medicine, but normally those reactions are in liquid phases. So then they have to first reduce the water content, or if water is not involved, then they have to dehumidify their medicines, and then they have to dry in order to make these small medicines, or small pellets, or small tablets. So drying operation is very much important there. Fertilizer industry, they use a lot of drying equipments. I'm not sure if you have seen, but in fertilizers we have around 200 meters, 250 meters high prill dryers, so that we uh, sprinkle our fertilizer like urea in terms of droplets, and using the air drying, we dry the urea in order to make prills, and then those prills are much more easy to be stored and handle, and they can easy to spread out in the field. So big equipments, big drying equipments that we use in fertilizers. We also use drying equipment in many other processes. So it is very important that you understand how the drying works, how we can calculate the energy balances around dryers. I will show you 2 or 3 main types of drying equipments. So the main learning outcome in this video discussion is that we will try to understand the drying principles and methods. We try to develop our knowledge on equilibrium moisture content and bound and unbound moisture. We will try to discuss very briefly the heat calculations that we do in drying equipments. It is very important that we understand the rate of drying and why it is vital, and also different types of dryers. First, before we go into details about drying, it is very important that we distinguish between evaporation and drying. As we have discussed earlier, evaporation is a process where we remove a large amount of water, and normally water is removed as steam or vapor at its boiling point. But drying involves relatively small amount of water that needs to be removed from a wet solid material. And normally we can remove water as a vapor by air. Water can be removed mechanically. We call it mechanical dewatering. And we can also use thermal methods so that we increase the temperature directly or indirectly of the wet solid, and then we try to help the evaporation works faster in order to remove the water from the wet solid. And we can also try to do it like this, that we try to heat up our air or gas and before it enters the drying equipment, so that there is a heat transfer from the hot air to the cold or relatively lower temperature of the solid wet solid material. But we have seen from experience that the mechanical way is much more cheaper than the thermal way. But mostly when we do the drying, we use thermal because it's much more easy to handle. When we dry a material, when it do not contain a significant amount of liquid or water, then we normally call that particular material as a dried material, but we can also call it bone dry material or bone dry solid. Typically when we dry our coal, it still contains a little bit of water, about less than 4% of water, but we still can assume that it's a dried coal. But in order to make it bone dry, it is possible that you have to decrease the water content less than 1%. The table salt that we use in our daily life, when we dry it, normally it has about 0.5% of the water content or a moisture content. Similarly, we also dry milk protein. They normally contain 8% of water. So in our daily life, we use many different types of dried products, dried food. And we have been using drying operations since centuries. Many people that like in the early 200 or 300 centuries, they used to do it like this, that they normally dry their meat. They dry in the sun so that there is no moisture or water content in the meat, and they can store it for as many time as possible, because they do not have freezers or fridge in order to store their food. So normally what they used to do, they just dry their food and then just use it afterwards. Normally they used to dry their materials in the summertime from sun, and they use it in the winter. So they have been using drying as a preservation technique for many years, and they try to reduce the water content less than 10%, because at this much amount of water content, the microorganisms and enzymes, they do not cause that particular or big chemical change in the food that we use, right? Normally if we have less than 5% of water content, It helps us to preserve flavor and nutrition in the food. So normally the products that we use, flakes, granules, crystals, powders, right? These kind of products, normally they have been dried before we can use them as a usable product. There are many methods of drying, and normally we can differentiate them or classify them based on their operating procedure. Like we can have drying in a batch process, we can have drying in the continuous process, drying performed for a given period of time and product collected in the end, it's part of the batch drying. But in the continuous drying, we dry our material continuously. So we add the material continuously, the wet solid, and then we remove our dried solid continuously from the dryer. So these are based on the mode of drying. So batch drying and continuous drying. But we can also differentiate dryings in terms of their physical conditions in order to add heat or remove the water vapors. One method is air drying, which is the most common method that we use in our chemical process industry. So in air drying, we have a direct contact with heated air at atmospheric pressure. So the wet material and the dry air, they come into contact with each other. If the air is heated, so the heat will transfer from the air to the wet solid. It helps to evaporate the water much easily, and the mass transfer will happen from the wet solid to the air. So there will be opposite direction of the transfer in terms of mass and in terms of temperature or in terms of heat transfer. We also use another method which is called vacuum drying. So in this kind of drying, we have rapid evaporation of water using a low pressure, less than the atmospheric pressure, and we use indirect addition of heat. So we can add heat by contact with metal wall or through radiations. These kind of drying that we use for many heat sensitive materials or heat sensitive food materials. For more heat sensitive material, we also use another drying technique which is called freeze drying. So freeze drying is something that water is sublimed from the frozen material, right? So the water is not first converted into the liquid, but it directly goes into the vapor phase, or then we dry the material and then we froze it. There are different ways in order to make air or gas in contact with the wet solid. One method is that the gas or the air flow across a static bed of solid, right? So we try to make it like this, that we have a contact of air or gas to the upward surface of the solid material. In this way, the topmost layer of the solid, it becomes dry, and due to the capillary action, the water content that is present beneath the surface, then it goes up and it keeps on drying. uh, this method, it is a relatively a slow process of drying. This is also a process in which air or gas pass through the bed of the solids. So we try to increase the contact between the air or the gas to the wet solid. There is another method that we normally use in rotary dryers. In rotary dryers, we do it like this, that we have a drum and then we put our wet solid material inside and we roll the drum. So when we roll the drum, the material or the wet solid, it keeps on falling from top to bottom. And during this time, we make the air to contact with these kind of materials, like sprinkling the materials inside the rotary dryer. So in this way, we dry our material. This is quite similar to what we do in our normal home dryers when we dry our clothes. This is also a very important way of solid handling, is using the fluidized bed system. So what we do, that we put our air or gas at a sufficient pressure so that it can withhold the solid material. So it has a certain pressure. And then what this air or the gas, it fluidize the wet solid. And then it have a very nice and uniform contact between the air or the gas with the wet solid. And this way that we dry our wet material. There is another method that we use in pneumatic conveyors. So in this way, we have the gas and the solid material, they go in the same direction. That is why it is called co-current gas solid flow. So in this way, the material, the wet solid and the air of the gas, they move together, and then they there is a possibility of heat transfer and mass transfer inside the dryer. But when we discussed about the principles of drying, it is important that what happens when a wet solid is brought into contact with air, right? So there are two possibilities. Whenever we have a wet solid brought into contact with air, the first possibility is that solid will lose moisture to air when air has the lower humidity. So if the air has lower humidity than the moisture present in the wet solid, there will be a mass transfer of water or moisture content from the wet solid to the air. But there will be another possibility. If the air has higher humidity than the wet solid, so what will happen? The mass will still transfer because there is a driving force available. So what happened? The moisture from the air, it start penetrating into the solid. So the solid will absorb moisture from air, right? So normally in drying operations, we try to keep the humidity of air or humidity of the gas much lesser than the moisture or humidity of the wet solid. And this process keeps on going until the driving force is like collapse or like it's done. Then there will be the mass transfer until equilibrium is attained. And at that point, when the equilibrium is attained, we call that moisture as equilibrium moisture content. And we can show it in terms of kilogram of water per kilogram bone dry solid. This is in terms of the dry basis. We can also call it in terms of kilogram of moisture per kilogram of wet substance. This is in terms of the wet basis, or kilogram of water per, let's say, 10 kilograms or 100 kilograms of dry solid. So we can denote the equilibrium moisture content in many different ways. And there are two main variables in drying. One, the humidity of air, and the moisture content of the solid. In drying, we always would like to have the humidity of air less than the moisture content of the solid, so that the mass transfer should happen from the solid surface to the gas surface. These are the temperature patterns in the dryers. So this one is for the batch dryer, and this one is for the continuous counter current adiabatic dryer. So what happened when we start the drying at time, any time which is like zero before we start drying? So we have a certain inlet temperature of the solid material. So when we start the heating the medium, heating inside the dryer, so the temperature of the solid abruptly changes from TSA to TV, which is the vaporization temperature. And this temperature remains quite constant for a certain period of time, and then it goes up till TSB. And normally in the batch drive, we have the heating medium, or heating from the air, heating from the gas, or electrical heating, any different types of heating mode that we use. We keep it the heating medium at a constant temperature. But in the continuous countercurrent adiabatic dryers, we do it like this, that the profile for the wet solid, it remains typically the same, or the cycle remains the same. But we have countercurrent of the flow of the gas or of the air. So the temperature of gas or air at the inlet is higher at the inlet, and then it is a little bit lower than at the outlet of the dryer. So we have a countercurrent system in the dryer. You can also have co-current adiabatic dryers, but there is a little problem because the driving force keep on decreasing as we reach the final stages of the dryer. And I believe that this is what you have also learned in heat transfer, what we call the temperature profiles and the concentration profiles in the mass transfer. So this is similar, that we have countercurrent system or the co-current systems. This is just to show you the equilibrium moisture content of many different types of materials. If you can see this is a curve for like a paper or newsprint material. This number 2 curve is for a wool, which is a little bit like porous material. This number 3 curve is for silk, and we can have for kaolin, and then we can have number 5 for the soap. And it is very important for you to understand that the equilibrium moisture content varies with the nature of the material, nature or type of the material that we are working with. And normally the non-porous insoluble solids, they normally tend to have a little low equilibrium moisture content at given humidity. And equilibrium moisture content of the solid decreases with increase in temperature at given humidity. And we also have to understand the concept of bound water or bound moisture and unbound water or unbound moisture. So if you look at the curve for number 2, which is for wool, so at this point we have 100% of the relative humidity. So at that point we have bound moisture. So the moisture content that normally indicated at the intersection point between the equilibrium moisture content and the 100% humidity line, this is the bound water. And this bound water exerts vapor pressure less than that of pure liquid water at the same temperature. And any water content or a moisture content excess than this moisture content is called unbound moisture content or unbound water. And normally it exerts vapor pressure equals to that of pure liquid at the same temperature. Now I would like to show you some curves that we use in rates of drying. So these are typical plots of total moisture content and drying rate versus the drying time. This curve A is the total moisture content. As the time passes with the drying operation, the total moisture content rapidly decreases and then it becomes constant after a certain period of time. This curve B is for the drying rate. First, as the time passes, we have an abrupt or rapid increase in the drying rate. And then we achieve a certain constant drying rate, and we call it constant rate of drying. So this constant drying period, after this point, what will happen? The drying rate again falls. So first it goes up, then it becomes constant, and then it falls. And this point is called falling rate period. This is just to show you the drying rate curve for a non-porous like clay slab. So what will happen? The drying rate first goes up and then becomes constant. But if we are reducing the moisture, so we start from A. So first we have a constant drying period, and then we have this falling rate drying period. And similarly, we can show the drying rate curve for porous ceramic plate. So first we have a constant drying rate period, then we have a falling period, and this point is called critical, and then we again have further reduction in the drying rate. Now, the most important part in dryers is about calculation of heat duty or calculation of energy balances inside the dryers. It is very important that we need to understand that we normally provide heat in order to accomplish many different types of processes inside the dryer. We first heat the feed that contains solid or the liquid. This is what we are talking about, the wet feed. So first we need to heat the feed that includes solids and the liquids to the vaporization temperature. We have to vaporize the liquid. We have to heat the solids to their final temperature inside the dryer. We have to heat the vapors to its final temperature, and we have to heat the air or any other gases to its final temperature. So there are different types of heat that is required in the dryers. First, heat the feed that contains solid and the liquid to the vaporization temperature. Then we evaporate the liquid. We need heat in order to increase the temperature of the solid to their final temperature, heat the vapors to their final temperature, and heat the air to its final temperature. But it is very important that the most important or the most significant amount of heat energy is required for only one process, which is the vaporization of the liquid. So this is the most important heat that we need to calculate. All other heat that is required in the dryers, they are quite little as compared to the liquid vaporization. But we have to consider them as well. But this is just for your knowledge that vaporizing the liquid requires a lot of heating as compared to the other important aspects in the drying operation. This is a basic energy balance equation that we use in order to calculate the heat duty. In this equation, we have QT over MS, which is the quantity of heat transferred per unit mass of the solid, right? So we have to calculate in terms of specific heat, and we also calculate the latent heats. So TSA is the feed temperature, TV is the vaporization temperature, TSV is the final solid temperature, TV is the final vapor temperature, lambda is the heat of vaporization, and then we have specific heats for the solid, specific heat for the liquid, and specific heat of the vapors. And then these XA and XB are the initial. XA is the initial liquid content, and XB is the final liquid content, and we can denote it in terms of mass of solid, mass of liquid per unit mass of bone dry solids. So this is in terms of the dry basis. In adiabatic dryers, normally heat is transferred to the solid, liquid, and vapors that normally come from cooling the gas. So heat balance for continuous adiabatic dryer is like similar to what we have, this Q is equal to mCp delta T. Here Qt is the heat that is required in the adiabatic dryer. Mg is the mass flow rate of the dry gas. CSB is the humid heat of the gas. THB is the inlet temperature of the hot air or hot gas, and THA is the outlet temperature of the air or the gas. And normally, whenever we do the heat balance in dryers, we have to include the heat balance for each section in the dryer. So heat transfer equation applies to the preheat section. The heat transfer equation will apply to the section where most of vaporization occurs, and to a section where solids are heated to their final temperature. Then again, we have the heat transfer equation, Q is equal to UA delta T. And U is the overall heat transfer coefficient, A is the heat transfer area, delta T is the every temperature difference, and Q is the rate of heat transfer in each section of the dryer. So for drying processes, and in order to size or in order to design our dryers, there are different things that we need to estimate. Either we need to estimate the size of the dryer, we have to find the operating conditions in terms of H or T of the air, operating time that is required to perform the desired drying. We have to determine the equilibrium moisture content that we normally determine experimentally, and we also experimentally determine the drying rates. And this is the equation that we normally use in order to calculate the rate of drying or rate of evaporation. Normally, this equation is very much important. In this equation, we have the heat transfer coefficient, and this is the delta T, and the area, and the lambda is the latent heat temperature Ti. And if we would like to calculate RC, which is the evaporation per unit area, so we can calculate for HY, delta T, and lambda. And we have to calculate the heat transfer coefficient. Normally, there are number of empirical equations are available in order to calculate the heat transfer coefficient. So let's say when the flow of gas or flow of air is perpendicular to the surface, and the air velocity is between 0.9 and 4.5 meter per second, we can use this empirical relationship in order to calculate the HY. G is the mass velocity. Normally, this kind of equation, we can have it in terms of British units, but we also know the empirical equations for SI units if we would like to calculate the heat transfer coefficient in terms of watt per square meter per Kelvin, right? So the first equation that you can use when air is flowing parallel to the drying surface, and the second equation that you can use when air is flowing perpendicular to the drying surface. And there are certain limitations for these empirical equations, that these equations can be used when the temperature is between 45 to 150 degrees C, the mass velocity is between like 2500 to around 30,000 kilogram per hour per square meter, or velocity is between zero point 0.6 to 7.6, or at least by 8 meter per second, right? So you can use these empirical equations in order to calculate the heat transfer coefficient, and using this equation, you can calculate amount of water evaporated per unit area. Right now, I would like to discuss some drying equipments. Before I go into the discussion on drying equipment, I would like to ask you that if you have any questions on how we can calculate the heat duty, or if you have any other questions. Do we have any question? All right, then I'll just briefly discuss some of the drying equipments or dryers that we use commercially or industrially in many different types of chemical process industry. The one most important type of dryer is called tray dryers. It's a very simplified version of drying. What we do that we stack our trays one above another, and then we put our wet material into these trays. We allow the gas to pass through or pass over these trays, and then the wet like or more humidity of the gas, it will go up again, and we have a recirculation as well. And after some time, we take out the humid gas outside from the tray dryers. So normally the solid material is spread out in a very thin layers, and these thin layers can be 1 centimeter, can be 5 centimeter, 10 centimeter, depending on the size of the dryers. And normally we have heated air that is recirculated by using a fan or a blower. Most trays are also heated by air that remove the moist vapors, and normally we use these tray dryers to dry pasty or lumpy solids. Another type is screen conveyor dryers. In these type of dryers, we put our material onto a conveyor belt, and then we use fans at different places inside the dryer, and we allow the air pass through like to the cross section of the conveyor belt, so it passes through the wet material in order to achieve a good mixing or good contact between the wet solid material and also with the air. So through using a conveyor belt, we dry our material and we keep on drying. So we enter our wet material here, and then after drying, we take out our material from that other side. And there are many different configurations of screen conveyor dryers. Another important type of dryer is tower dryer. In this tower side, we have trays on the two sides of the dryer, and then we have a working shaft that helps us to rotate the system. So normally we have the turbo system inside the tower dryer. So what we do, we put our feet at the top of like the topmost of the tray, and then we scrap our material to the next tray and next tray, and then it keeps on falling, and then we can have a discharge from this point of the dryer. This is also very important type of dryer that we use. But one problem with this dryer that it consumes a lot of mechanical energy. So we normally dry those materials that requires drying at a very fast pace or in a more continuous way. Another important type is fluidized bed dryer. In these type of dryers, we use air or dry gas, and that it fluidize the material. So the drying gas should have a sufficient pressure in order to hold or fluidize the wet solid material in a fluidized state. And there are certain advantages. Normally, we have a high heat transfer rate. We normally have higher heat transfer coefficients, and we have a short drying time that is required in the dryer. And normally, due to the fluidization, we can have a good control of drying conditions inside the dryer. Right. So I would like to ask you that if you have any questions on drying operations. It's a rather very simple way of separating the moisture from the solid, and it's quite easy to understand and easy to visualize. But I would like to ask you that if you have any questions, please ask. I have also suggested, recommended or suggested or recommended problem for drying, and maybe I can show you. So I have recommended two problems for drying. And the first problem that you have, that you know the wet bulb temperature and the dry bulb temperature, you know the length and the width and depth of the dryer. The heat is transferred by convection, and it is important that air is flowing parallel to the surface, so that you have to use the heat transfer equation, not heat transfer coefficient, calculated from the right empirical equation, and then you have to calculate the rate of drying at constant rate, and we know the velocity is like this. And similarly, you have to make the calculation on total heat transferred in the dryer when you know the conditions. I have also added their solution into the canvas, so you can try to use the equations that I have showed you in the PowerPoint. So the same equations that you are going to use to solve these problems. So I suggest that you try to solve by themselves, but you can also consult the solution that I've already included in the canvas. Okay, and I also receive a question about that, will it be a home assignment for distillation? Yes, I will add a home assignment or a home exam for distillation. I will also add a home assignment and home exam for drying as well, right? So from my side, you will have 4 assignments, one on evaporation, one on humidification, one on drying, and one on distillation. And I will upload them as soon as possible. Hopefully for distillation, I will do it today or by tomorrow. And there is also a question that if I can explain the first question of the humidification on the home assignment. Let's see. Okay. So okay, so there is also a question from one of the student is about that if I can very briefly explain the first question in humidification assignment. So the first question is about is a theoretical question, that how you can assess the performance of a cooling tower. So when we say performance of a cooling tower, how you can access in terms of if the efficiency can be calculated, or if you can calculate it, how much is the temperature differences in the hot water coming into the humidifier, and how much is going outside the humidifier or in the cooling tower. So this is what you can also search from the web, or you can find the answers to this question from the book. And why you have to also think about why we have to estimate the range and approach in order to evaluate the efficiency. We have discussed the range and approach as well, but you can think about that why it is important to estimate range and approach in order to evaluate the efficiency. So this is a theoretical question, so you can refer to the book chapter, you can refer to the internet, and you can find the answers, and you can write the answers in your own words, right? And the other question is quite simple. You have to use the psychrometric chart in order to calculate the relative humidity, specific humidity, enthalpy, and dry bulb temperature, and the dew point. So it's a quite straightforward assignment, right?
I'm sorry, our internet broke, so I couldn't really hear what you said on the first assignment.
Okay, maybe I can repeat it again, no problem. Okay, so I'm not sure that if you have listened at what I said. So I said that from my part, you will be having 4 home assignments. There will be one home assignment which I have already put regarding evaporation. I have also added one home assignment, or you can call it home exam, for humidification, and there will be 2 more home assignment. One home assignment will be on distillation, and there will be one more assignment on drying. For distillation, I will try to add the home exam or home assignment hopefully today or by tomorrow, and then I will also upload the home assignment for the drawing. The reason that I have not added that assignment is that I wanted to give you some more time so that you can try solving those recommended problems. So when you solve those recommended problems, it will be much more easy for you to solve the home exam or home assignment for that particular separation technology. And there was a question on that if I can explain the question number 1 in the home exam or home assignment for humidification. And the first question was that how you can estimate, how you can assess the performance of a cooling tower. You can find the answers to this question from the book, and you can also find the answer to the questions from the internet, that how we can evaluate that if a cooling tower is performing well, or if the cooling tower is not performing well or not according to the design. What could be the reasons that if we have designed our cooling tower for a certain range and approach, why it is not performing according to the design specification, or how we can evaluate, how we can find that if a particular cooling tower is working well or is not working well. And the second question was that how you can find that range and approach are important in order to evaluate or estimate the efficiency of the cooling towers. I have discussed that how we can calculate range, how we can calculate approach in the cooling towers, and you have to answer theoretically that how you are going to use the information or the knowledge from range and approach in order to evaluate the efficiency of the cooling towers, right? Then you can find your answers and you can write theoretically in your own words, why do you think that we would like to estimate range and approach in order to evaluate the efficiency of the cooling tower, and how you can assess the performance of cooling towers. It could be based on design parameters, it could be based on efficiency, or so many different parameters, but you can search from the web and from the book as well. The second question for the humidification was very straightforward, that you have to use the psychrometric chart in order to calculate the relative humidity, specific humidity, enthalpy, dryable temperature, and dew point. This is what we already have discussed in humidification. So it's a very straightforward home assignment for humidification.
I have a question.
Yes, please.
You said you were going to release the, what's it called, labbarna next week or something. Is that going to, how long do we get to fix those? Because we also have these assignments. Are those going to be on the same time period and or whatever? Because that's going to be a lot to do, I think.
Yeah. So the thing is that you will be having your lab assignment next week, and this is not a very large lab assignment, because since you will be working in groups of 3, and normally students in the past have been doing those lab assignments within 2 or 3 hours. So within the same day, you can perform your theoretical lab assignment for the first theoretical part, and the next day you will also given some actual data, and then you perform the same calculations again using the same data. So those lab assignments will not require more than, like, let's say in total, it should not require more than 6 and 7 hours. And then you are done with the lab assignment.
Okay.
Yeah. And the information on the lab assignment, I will add the material within this week, and you will perform those theoretical calculation on distillation on, I think it is on Monday. Let's see if in the course plan. Yeah, so it will be on 18th of May. So you will be performing the lab home assignment on the same day. So that's why I'm suggesting that you perform the recommended problem for distillation before you come to these home lab assignments, so that it will be much more easy for you to handle. And normally students can perform those assignments or those calculations not more than 3 hours or let's say 4 hours. So hopefully you can perform those calculations within the same day. And I will be available, and I think Bjorn will also be available during those sessions. So if you have any question while you were working in groups, so you can always ask questions, and then we will also help you providing some hints if you get stuck in solving those smaller questions around distillation. So it will not be that much. Do we have any more questions?
I have a question on the evaporation assignment.
Yes.
We are giving a value for CP, and I don't understand if you were going to use it.
Sorry?
In the assignment, we are giving a value for CP
Yeah.
that we don't need. Or do we need that to do the assignment?
It is in the lab home assignment, or is it in the recommended problems?
The home assignment.
You mean the home exam assignment, right?
Yes.
Yeah, but I cannot comment at the moment because everyone is working on those assignments. So you have to figure it out by yourself. But when you submit your assignment, then I will comment that if you have done it right or wrong.
Okay.
And it is normally, it is if you feel that the CP which is given in the problem, it is not necessary. Sometimes it is given that if it is necessary, or sometimes it is not given. It completely depends on the question. So you will do it as whatever you feel that how it should be done. If you need it, then use it. If you feel that no, there is no equation that you are going to use that requires CP, then don't use it. But I can comment on this lab home assignment after everyone has submitted those assignments.
Okay,
And then I will give you comments on your assignment individually, and then you will have an opportunity to redo your assignment in case if your assignment is not right. Right? Do we have any more questions? If we do not have any more questions, then I will say goodbye, and I will
get every assignment at the same time.
Sorry?
Do we get every assignment at the same time back from you?
Sorry, I did not understand your question.
Do we get every assignment back from you at the same time?
You mean to say feedback?
Yes.
Yeah, for the feedback, we have done it like this, that I will, Jorgen is going to put a deadline, like a final deadline for submitting his assignments. I think it will be very soon. So he will add those deadlines, and after that deadline, he will start giving you the feedback for each assignment, and it will be given to you. And it will be similar for me. I will make a final deadline. After that, the deadline is finished, and then I will give the feedback on your each assignments. And then if your answer or if your assignment is not correct, you will have an opportunity to redo your assignment in order to pass that particular assignment. Because we are still receiving the assignments from many students, but we have to put a certain deadline that after that time, then you will not be allowed to send in your, like, let's say, first draft of assignment. Right? I'm not sure if I answered your question, or if that was your answer, if that was your question.
Thank you.
Yeah. All right. So do we have any more questions? All right, then I will say goodbye and wish you good luck, and I will see you next week regarding the lab assignment, right? And I suggest again that please do your distillation, so that it will be much more easy for you to work with the lab work, right? All right, thank you so much. Have a good day. Bye.